So, we have done the clause theorem which says that for a strictly non-blocking switch R2 has to be greater than or equal to M1 plus N3 minus 1, and of course, if the switch is symmetric, M1 should be equal to N3 is equal to N, so it will be 2N minus 1. So, that was we did in the last video. Now, this particular condition is not the condition if I am going to look into multicast scenario. Okay. So, before I go to the multicast scenario, let me set up a condition and show that yes, it does not happen. So, we will actually take up an example first to exemplify whatever I have taught in the clause theorem. Okay. So, and then of course, we will come over to the multicast case, and we will try to exemplify that in multicast case this whole theorem actually breaks. This same condition is not good enough, and then we will try to see if how we can determine a condition for a multicast scenario. So, I will get a crude bound, there are 2-3 more estimates which are there. So, we will not do that thing in detail, but you can look at the papers which are put on the Brahaspati site which has been listed in the forum, and then actually go through those papers to understand how those conditions are being derived in those research papers. So, I will give a very crude estimate of F-wave multicast. So, before that, so let me take up a small switch, it is a 3 by 3. And show you that when I will be able to set up a connection, and any path which have been already set up should not be disturbed. Okay. If I am allowed to do a rearrangement, I can actually do at much lower thing. So, that will be our next theorem. So, let us put 3 switches here. So, I put everything 3 by 3, so this also has to be 3 by 3 now. So, it is a 3 by 3 multiple 3 stage switch. So, 9 by 9 basically clause. Now, let us see when the blocking will happen, and I will keep on increasing this, and ultimately every time I will show you that there is a blocking, and when this condition of 2 into 3 minus 1 which is 5, when my number of middle stage switches will become equal to 5, I can always set up a path between free incoming and free outgoing port. I will just create worst case scenarios. So, the case here is very simple, I want to actually have I here. I will also draw corresponding pulse matrix. Okay. So, this is the output which I want to connect. Now, can I create a scenario where the input and output cannot be connected? So, I have to just create that scenario and draw a corresponding pulse matrix. So, I will have a switch identifier as 1, 2 and 3 here. Okay. And I am only worried about the row corresponding to this switch and the row column corresponding to this one. So, again these are 1, 2, 3. So, the pulse matrix here will look something like this, it will be a 3 by 3 matrix. So, this is the switch 1, 2 and 3, and these are in the third stage 1, 2 and 3. Okay. So, I want to set up a path. So, if this path has been set up in this fashion, the first is, I am just going to create a blocking scenario, and let us see what will happen. The second one is being occupied through this. Okay. The third one is can be in this fashion, and so now the connections the way they are actually happening, let me use a colored chalk. So this connection is connected already, so these lines are occupied. Okay. So from this side these two are occupied, the third one is which is free, which can be used to connect this input to the output. Okay. So the only switch which can be used is this one, but what I have done is I have connected this output through this to this one. Okay. So I have consumed this particular path which was required, this was the only path through which you could have set up this I to O connection. So there is a blocking which has been created. Okay. So now you look, these are the 1 2, these are 1 2, there is only one which is overlap, there is no free middle switch which can be used to connect input and output. What is the corresponding pulse matrix? So pulse matrix, from 1 I am connecting to 1 via 1, so I will put 1 here. From 1 I am connecting to 2 via 2, so I will put 2 here. The third is being connected to third via 2, third is being using third to connect via the third one to the second one, so 3 is here. Only elements which are available are 1, 2 and 3, which are the middle stage switches. Look at the row, they contain M1 minus 1 in the worst case scenario. So which is 3 minus 1, which is 2 elements, 1 and 2. Okay. There are actually 3 elements, but 1 and 2 have been consumed, the third one was available. In the column, since N3 is equal to M1, so its N3 is 3, so again 2 elements have been occupied, but this time it is 2 and 3. I need to put something here. So do I have a free element? I have only 3 elements, 1, 2 and 3. So union of this, which is your AE in this case is 1 and 2, BE is in this case is 2 and 3. So union of these two will give me 1, 2 and 3. I do not have any free element to put, so connection cannot be set up, it is a blocking switch. Now if I increase the number by 1 in this example, I can make it 4. Now interestingly the switch is no more going to be 3 by 3, it will be 3 by 4, 3 by 4, 3 by 4, these will become all 4 by 3 switches. Okay. Intermediate switches will still be 3 by 3, so this will also be 3 by 3, but there will be 4 elements now. So I have to now connect from here in this fashion. Now can I still create a blocking system here or not? So let us see, what I can do is, I have 1 and 2 has been occupied here. So if this by chance is not using this particular path, but it may decide that I am going to set up a path in this fashion, from here is all the way here and then in this fashion. So what I will have is, I will have this as occupied link, this as occupied link, this is occupied here. So the changes in the pulse matrix, now I can have 4 elements in the pulse matrix. Okay. So I will have 1 and 2 here, and this will contain, instead of 2 this will become 4. So I have 1 2 and 3 4. So union now consists of 1 2 3 4. oh, in this scenario again I cannot set up a path between the two. Okay. Reason being, again my number of elements are not satisfying the clause condition. I can increase one more now because that is the limit which comes from the clause theorem. So, if I can put another one which is the fifth element. So, each one of these switches now will become 3 by 5, this will also become 5 by 3, these still remain 3 by 3 but 5 switches. So, I can now connect in this fashion. So, now since these two and these two are do not have any overlap, even if this I actually start try in any way to occupy. So, if I actually instead of here I want to connect this one through this last one, then I will free up this one actually and I will end up in connecting this. So, there will be always one free switch which is available which can be used for connecting input to output. I will be able to make a connection if I have 5. What does that mean? I have 1, 2, of course the last fifth one is being used, so it is the 5. So, it will become 3 and 5 which have been occupied. Union consists of 1, 2, 3, 5. There is element 4 which is available which can be put here, that is what I had done, and total now cardinal, this is now satisfying the condition given by clause theorem. Okay. And this actually gives an example, there is a proof that yes, clause theorem does hold true. So, you can actually try different examples and see, and you should be able to create the blocking system. If my number is not matching this, the moment your R2 is less than this, you can always create a scenario whereby switch is in the blocking state. So, I can take up one more example, this time I am doing it extempore here itself, but I will take the dimensions which are different and prove that I can create a blocking system. In fact, if you are clear about the theorem, intuitively you should be knowing that how this has to be done. Okay. So, let us take a small example. So, this time I am taking 4 by 4. I have taken a symmetric system here, this time I am taking asymmetric system. Okay. So, I am going to use 4 by 4 3 switches. Okay. And this time I am using here on this side not 4 by 4, not 4 inputs, but say 3 inputs. Okay. So, I need some middle stage switches. So, as per clause theorem I require 4 plus 3 which is 7 minus 1, at least 6 switches will be required. So, I can put 5 of them. So, I do not have 6 and I will be able to, I should be able to create a blocking scenario with 5. Okay. So, each one of them will be connecting here. So, the switch size is 4 by 5 and this is 5 by 3. Okay. So, okay, let me do it actually completely. So, all middle stage switches are 3 by 3, all of these are 3 by 3. In this fashion. So, if I want to connect for example say this one which is the input and this one, I can take arbitrary anything, this is the output. I have to just prove that there is a blocking condition here. So, it is not a strictly non blocking switch, that is good enough as a proof. So, if I want to do that, I will take these 3 and they can be connected to anything, anywhere actually. So, this is occupied, this is occupied. In fact, I need not bother because I should only look at these links which are occupied. This one is occupied, it is okay, and the output links which are emanating from here. So, next one I can connect via this and connect to any incoming anything. So, this link gets occupied and there are total 5 links, remember. So, third one I can take this. So, this link gets occupied. Okay, only these 2 are free. So, there are only 2 links which are available here. So, I need to just prove that the 2 links which are connected to this, only these are the possible links which can actually be used to set up the connections. If these are somehow occupied, then it is not possible. So, I can set up a connection between already existing path. So, this gets occupied to some path here. I can use other one to connect via this to this one. Now, you can see these 2 are occupied and these 3 are occupied. There is no free intermediate switch by which a connection can actually be made. This is a blocking system, and how the pulse matrix will look like? So, in fact, you can actually do it for any arbitrary system. In this case, it is a 3 by 3 pulse matrix. You will have, I call it number 1, 2 and 3, I call it 1, 2 and 3. Okay. These switches are 1, 2, 3, 4 and 5, and they do not satisfy the Claus theorem. So, you can actually look at, I am looking at this 2 versus 1. So, 2 is already occupied, 2 has actually connected via 1, and this is for the third switch. 2 is connected via stage 2 for the second switch. 2 is connected via 5 to the stage 3 switch, and look from this one side in the column, there are 2 elements which are missing here. See, you cannot have more than 3 in this case, m1 minus 1. So, from here it will be again n3 minus 1, which is 2 here. So, this 1 is getting connected via 3 to 3, and the next one it is connecting via 4 to 1. So, set AE in this case is 1, 2 and 5, BE will be 3 and 4, union of these 2 1, 2, 3, 4 and 5, no free element available, you cannot set up a path from input to output. So, that is again a blocking system. The moment I add one more 6, and this is a worst case scenario. So, remember these 2 are connecting to these switches, these 3 are connecting to a different one, and their sum total is equal to total number of middle stage switches. I created one extra which is free. Now, this can always be used to set up the path, and when I put it, make it equal to 6, this satisfies the Claus condition. So, it will be 4 plus 3 m1 plus n3 minus 1, 4 plus 3 is 7 minus 1, which is 6, 6 number of switches. It will enable the path to be set up. But remember, in real life world we do not actually create strictly non blocking switches, we always create blocking switches, controlled blocking. So, that amount of hardware you save on the switches hardware, and with limited blocking you reduce the cost of the switch. So, now let us come back to the multicasting scenario after this example. So, in multicasting what is going to happen? So, let us understand how the multicasting happens in a 3-stage system. So, now let us look at the equivalent of a Claus theorem for a multicast system. So, in this case, first of all we have to understand when a multicasting happens, how it happens in a 3-stage system. So, when we build up a switch, so normally a switch will have the first stage, the second stage and third stage, that is a closed configuration. So, how the multicasting will happen in this case? So, multicasting basically means there is one input and I would like to connect it to multiple outputs. So, there is only one transmitter, there are multiple receivers. Now, if you look at here, from one line I will be able to get the signal from the input here, and I can, because it is a broadcast, is a crossbar system. So, in a crossbar, when I want to do a multicast from 1 to say all the ports, I just snap all the cross points together. So, the duplication or multiplication in a multicast system happens within the crossbar. So, one input can be fed, can be feeding the two outputs, and so this is a strictly non-blocking system. So, I should not worry about the multicasting if the multiple inputs are here. Okay. So, for me, even if there are multiple inputs, multiple outputs which have to be connected to same input, this is as good as I should only bother about that how I will be able to send the signal here. So, for me, I will define something called a multicast, the way the F-wave multicast we call it. So, this actually means the number of switches in worst case to whom, in the output stage to whom I need to copy my input. So, that is a F-wave multicast. So, this number is F. So, I am giving a very crude estimate of how many middle stage switches will be required for implementing this. Of course, this can actually be refined further. So, in this case, now there is one possibility that I actually can take a signal here and split it here itself into multiple copies, send it here, then I can do a split again and send it to the multiple places. In this fashion. In general, this is what is actually going to happen. Okay. So, that is the case which we need to actually essentially now use Paul's matrix to figure out an estimate of how the F-wave multicast is going to work. Okay. In this case, if I draw the Paul's matrix, this is the switch from where the input is to be multicasted. Now, this can be multicasted to F different elements. Okay. So, these are various outputs. In worst case, F-wave multicast actually means there are F separate third stage switches or output stage switches. So, 1, 2 and F. So, what I need is I am not actually going to divide my signal here, I do not want to do that, I can certainly do that, but I am not considering the case. So, if I permit that, probably I can have a much more efficient multicasting. So, my bound actually will improve in that case, but I am not considering. So, this is not permitted, you have to just find out one switch, pass the signal on to that, and that will then connect to all F switches to whom you want to communicate. So, you have to find out when all these lines actually will be free, you have to just find out that middle stage switch. That is our strategy as of now, but in reality this actually estimate can be improved if part of these are permitted via this switch and part of it can be permitted via other switch, and we can actually get a better bound. Okay. So, this is possible, but I am actually doing it in a very simplified manner. So, there are F such possible output switches. Now, how many elements which can exist here? Remember, the two inputs cannot combine into one single output. So, all the elements have to be distinct here. So, number of elements which can be there is n3 minus 1. And if you take the worst case scenario, in that case number of elements which are here, all these elements do not have any overlap. So, if you create the union of these and find out that cardinality, that will be nothing but sum of cardinality of each one of these. Okay. So, basically if you take an intersection of any one of these f rows, f columns, it turns out to be null. So, that actually means number of elements in all these f columns will be f into n3 minus 1. Okay. And then of course, A is also communicating, so there is only one input port which is free. So, there will be remaining elements which can be here is m1 minus 1. So, if this m1 minus 1 elements and f into n3 minus 1 element also do not have any overlap, in that case total sum of the middle stage elements which have been occupied are f into n3 minus 1 plus m1 minus 1. But remember, I am talking about a f-way multicast. Okay. So, these many elements are already occupied. So, I need one element here which can be put in all these f columns or these cells, it has to be repeated, same element. So, in that case, if I have one element extra, I can just put it here, and then my R2 has to be greater than or equal to this, and I will be able to set up a f-way multicast in this scenario. Okay. It is independent of any other condition or any other multicast which has already been set up. Okay. I will always be able to set up a connection in this case. This is a worst case scenario which I have put. In fact, there can be multicasts which have been set up by other inputs of this A, but those will be done already with a different element, m1 minus 1 distinct elements which of course might have been repeated, but if we actually take only distinct elements, the duplicate ones are being counted only once, there will be m1 minus 1 already there present in this case. Okay. So, this is what is going to be my bound for a multicast implementation in a closed network. So, the earlier condition, so we had m1 plus n3 minus 1. So, this condition gets converted into this one if you want to actually have a f-way multicast. So, this will become f into n3 minus 1 plus m1, where f is number of output third stage switches to whom the multicast has to be done. I am not counting the number of ports here. Okay. So, if all the ports are being occupied and multicast is being done, so from one input technically I can get into f into n3 number of ports, that multicast is technically feasible. So, 1 to f into n3 ports, that kind of map is possible. Okay. So, this f parameter essentially governs that how many middle stage switches will be required.